I'm now going to talk about some, if you like, implementation details in Matlab referring to the use of what's called a callback function. And these are very, very useful things. And if you're going to do optimizations using some of the built-in Matlab functions, you do need to be aware of what the idea behind this is. So first of all, hopefully you know about functions already. It's very good practice to use functions. You can write things in a reusable way. Right? If there's something you want to do and you want to do it a lot, it's nice to have a simple function which you can write. For example, this is just to plot some data. I've written a simple function, plot data. It takes as an argument a matrix, and it does various things. It sets font sizes and it plots things out, puts titles and stuff on it. And as we know in MATLAB, when you write a function, you call it whatever you're going to call the function. I'm calling it plot data, and then you would save it in a file, plotdata.m. And it's actually the file name that really matters. You can actually put anything you like in the actual file here up the top by the name of the function. But then what you can do is you can then, provided it's in the path of the main script that you're going to use, you can then call this thing from a script, right? So you can then generate some data here, and then we can call this function directly, and it'll do something useful, hopefully. So functions are very nice ways of writing things, so you can actually reuse them very easily. Also, it's nice to split your code up into smaller chunks. So we can also have pointers to functions, right? So we can actually get a pointer by putting the @ symbol in front of a function name. And what that will do, it'll actually basically get the pointer to that particular function. And then, so if we say func pointer equals @plot data, what that means is it's setting func pointer to actually be that function. So we can actually then call this variable func pointer, and it will actually call the function that we actually set to be to do it. So we can call this, rather than using the name that we had originally, just using this actual name that we defined and then set equal to the pointer. And that's very useful because what we'll see is we can pass functions as parameters, and that's what I'm going to talk about now. You can pass functions to another function, right? So we can pass the plot data function to another function, right? So here we've got, let's say we've already written our plot data function. In the main program we might call gen data and plot, and this gen data and plot actually takes as an argument a function pointer, right? So it's getting a function pointer coming in. So now what I can do in the function, it's setting up some data, and then it's calling the function pointer of the thing we passed it when we called it in the first place. And the reason that's useful is because this is a nice way of installing things called callbacks. So what is a callback? Let's give you a very simple example using the graphical user interface. A lot of event processing in MATLAB, in fact, a lot of event processing in general can be nicely dealt with using callback functions. And a callback function is a function that gets called when an event is fired. And an event could be, we click the mouse button, for example, to change the appearance of a plot. So imagine we put in this function that sets the line parameters, right? We're going to generate this function. It's going to take, first of all, here a structure, and we're going to ignore what comes after it. When you're building this kind of thing, these kind of functions for specific functionality in MATLAB, you have to look at how it wants the parameters. But all I'm going to do here is I'm going to pass it in this function, which is going to be a callback. It's taking this structure source, and it's just saying source.color equals red. It's setting something red, and it's setting something to a line width of 6. So let's generate a plot now. We're going to generate a simple plot. We're going to use the plot command, and we're going to install a callback in the plot command. You can look in the help on this to how to do it. We're going to put a callback. So in other words, when I push the button down, it's going to call this function. And this is all defined in plot, how to do this. But you've got to supply this callback function, right? So when the plot command is called, it will generate a plot, and then when you click the button down, it will call the function that you've installed here, right? So initially, the plot would maybe look like that, because I'm just setting it up by default. I'm installing the callback, and when I click the button down, it will then call the callback, and then because when passing it some information about the plot, it's going to actually change and update the parameters. That's something you can easily try yourself. So that's just talking about callbacks, because like I said, that's something that we're going to use now in optimization. So optimization in Matlab, basically optimization, the idea is, and you can look at Wikipedia, it's basically, it says here, selection of the best elements. Basically, what we're going to be using it for is we've got a model of the world or a model of some data, and we have some free parameters in that model. And we want to know, how do we set those parameters such it's the best possible model it could be? So we're optimizing it. So basically optimization relates to maximizing or minimizing some function by systematically changing the way the parameters are such that we get the best possible values. It could be that, you've got a car. Let's say it's not, the engine is a bit of a mess. You might want to optimize it such that it can go as fast as it possibly can. So this might involve, tuning the engine up, putting on better wheels, higher grade fuel or something like that. What can you do to make this the optimum performance for any particular device? In mathematical terms, basically it's we're trying to find, let's say, a maximum or a minimum of a function, and in this case we've just got a two-dimensional function, and we could have parameters going on along the x-axis and the y-axis, and the overall performance could be the height we are up the z-axis in this case, in which case you'd see on this particular example we've got an objective function which is a nice convex thing. It's got a unique peak, a global maximum, and you could say, in terms of what we're deciding that this, what we're calling as being a good thing to optimize or a good performance measure, in this particular case, we probably want to find parameter values correspond to this point here at the top, this little blue dot. So this objective function tells you how well you're doing, right? That's what we can call it. The objective function is a function which tells you how good your solution is. It could also be how bad, in which case you want to find the minimum value. In the previous example of linear regression, for example, what we'd want to do is to find, the minimum error. So we're doing a kind of an optimization problem there. When we're doing iterative gradient descent, what we're doing is we're finding the optimum value of the gradient and the offset of the line to get the best possible fit, which minimizes, in our case, it was the summed squared error over the data set. Now, there's much more sophisticated things you can do than just a simple gradient descent. So we were just doing a simple step down, one at a time, down the gradient in the direction of the gradient by a certain step size. There's more sophisticated things you can do. We won't go into them. We won't go into them in this course. You can first of all look at things like second derivatives, not just first derivatives. But you can have systems which do all kinds of other stuff, jump around everywhere, sort things out for you. One particularly useful function in Matlab, and there's a whole range of them to find minimums or maximums of functions, is something called fmin_con, which basically refers to finding a constraint, that's the con, minimum, that's the min, of a function which can have multiple variables. And if you do help on this function, just so you're aware it exists, do help on this function, it'll give you loads of different ways of actually using it. This is a particularly useful one. X equals fmin_con. The first argument fung, that is going to be your a function which is going to do your it's going to basically, you've got to pass it a function which is going to be your objective function. Then you give it an initial value, and then you can pass it some inequalities, or so that it has to do things in a certain constrained way. So let's have a little think about how we could very briefly use this in order to do linear regression, right? So let's think about what would be a good objective function. Well, what do we want to do? Let's just think from first principles. So first of all, we want to get, well, first of all, this function, the way it works is it's got to be something that you're giving the parameters to. So you've got to be able to get at the parameters. So we're defining the first value here as the weight matrix, which is going to be, actually in this case, first element's going to be the gradient, and the second one's going to be the offset. And then we've got to do it across the data set, because we're doing linear regression across a whole load of data points. So I'm going to say I'm passing it my data, and this is actually a structure, so I can get from this the x value, right? So that's an array of x values, a matrix in Matlab, of course. And the second thing, dot target, that's the y value, that's a set of targets. And there's a certain number of them that we're actually doing it here for, right? So what I need to do now is I need to, in my objective function, I've got my data set coming in, I've got my m and my c coming in. I want to do my predicted y given the x's that are coming in from the data set. So I say y equals mx plus c, so m times x plus, and this is c basically. It's just, you know, given the fact that x is now actually a matrix of certain dimensionality, I can't just add a single one-by-one value of c on. I've got to change the dimensionality of the c and replicate it, so repmat, so I can actually add on a constant term to every other term I've got here. So this is all this is doing is calculating the estimated, it's y hat equals mx plus c. That's all that's doing. And we'll worry about the details when you start doing your own lab practicals. But then all we have got to do is like we did before. We said we want to define the error as, right, the difference between y, which is the actual target data we've got in the y or in the second dimension, and our predicted y. So y take away y est. We want the squared error. So we square every single value, and we'll see later on as well, this dot functionality means we're doing element-wise squaring. So we're not doing this as a great big matrix and then squaring the matrix. We want every element to be squared. And then we're summing them up. So this is summing up all the values across the data set. And then we're returning that as the error. Right? So we built this objective function suitable for linear regression, but just basically is just looking at, you know, the formula for error that we came up with in linear regression. It's the sum of the squared differences from the actual y value and the predicted y value, right? That's the important part, calculates error. So let's have a look at how we could pop that into Matlab using fmincon. Well, first of all, you know, you've got to, you know, there's loads of parameters on this function, unfortunately, most of which you can just set to empty matrices, so we just ignore them. So we're not going to have this a and the b. These are all the constraints and the lower bound, upper bound, non-linear constraints, all this kind of stuff. So the a, b, a, eq, b, eq, lb, ub, non-l con, all of those things, I'm just going to put the parameters in as null, as an empty matrix. What we do care about now, though, is putting in our data, right? So we need to put in our data as x and as in y. So the way we represented it within that function, if you remember, we had a structure dot capital X, and we're calling that the x data, and then we're having a structure dot target, we're calling it, equals our y data. So you could do this yourself and call this y. Then we call the function, we give it our objective function, we give it the weights, which are going to be basically containing you know, the m and the c. We give it all of these other parameters because we have to. If you look at the call in the help, we have to give it this options thing, which is also empty, and then we give it my data, which is my list of data, and then we run it. And what it returns is going to be, in the first element, it's going to be the estimated gradient, and the second term is going to be the estimated offset, right? And when we run that, basically it'll run and it'll give you some error messages. It'll tell you why it's ending doing the optimization. It's stopping in this case because it couldn't get any further. And then all I finally do, is print out, or plot out, first of all, the actual target data that I was using, and then I'm just to show you here, I'm not showing you the code, but I'm just plotting on top of the graph the found line, so you can see that it's all working.